Let's take a look at the N2F2 sequence. This would be nitrogen, triple bond, sigma bond, 2 pi bonds, sp hybridized, sp hybridized. Let's take and add a proton at this position. And that's going to make it into an oxygen. Now we have the NO, same triple bond, sp. At this point, the nitrogen formal charge is 0, the oxygen is +1, which most likely this form here is the bigger contributor, if you will, where you have the nitrogen +1 and the oxygen is 0, and sp hybridized. Let's take and add an electron. The electron is going to come to the oxygen. It's going to break a pi bond, 1 electron in here. This oxygen with the p orbital has a pair of electrons now, and there's 1 electron left here, and this is what we call a L-top along the p orbital pi, which has seen some models of that. But anyhow, this would be NO, sp hybridized, sp2 hybridized, a sigma bond, a pi bond, a traditional pi bond, and a 1 electron p orbital moved into the pi region. At this point, you can see that the nitrogen would be plus 0.5, the oxygen minus 0.5. So this would be the NO. We take and add an electron to the NO, and it's going to come over to this nitrogen. You're going to break this bond. At this point, again, 0.5 plus 0.5 minus. We're going to have, what happens here is this 1 electron is going to stay in that p orbital component of the pi, and you have here the nitrogen is going to be sp2 hybridized, the oxygen is sp2 hybridized, minus 1 and 0, and this would be a 1 electron p orbital pi bond, and this is 1 electron p orbital pi bond. This form would be minus 1, 0. We come over here to another form, which would be the electron on the oxygen in the p orbital, and now you have minus 0.5 and minus 0.5 for this one, and this would be a negative, NO negative, and this is going to be high energy because this would be the main contributor. At this point, we take and add a proton to the nitrogen, and that makes it an oxygen. And you can see here, this would be oxygen structure. sp2, sp2, a sigma bond, a 1 electron pi, and a 1 electron pi. And now the sp2, sp2, and now the charge on each oxygen is going to be 0. So this is the oxygen. Come down here, let's take and add an electron to the oxygen, and then we're going to add it to the one on the right, which I like to do. Add electron here, this electron now moves over in that area, and now you have O2 minus. Now, what happens here is that this one, you got a sp2, and pair electrons, a sigma. You got 1 electron in a p orbital pi. It's over in this pi region, and this pair of electrons is going to be in a p, or possibly an sp3. I'm showing sp3 here. I don't necessarily think that'd be true. But anyhow, it would be over here on the oxygen, pair electrons, and the charge is plus 0.5 and minus 1.5. Now, this would be formal charge. If we take and move this electron here over to this oxygen for p orbital, now we're going to have 0 for the formal charge on this oxygen, and we're going to have -1 here. And I think this is the structure it's going to have, because again, this negative charge is going to be on this oxygen here, and whereas in the oxygen here, each oxygen is pulling this lone electron into the pi bonding region, here this negative oxygen is going to be pushing, and it's going to make this one into a p orbital or into an anti-bonded orbital. So superoxide is very reactive, because again, you got a negative charge on this oxygen, and you have the electron in a p orbital, and that was the same situation that we had up here with this one. So these two would be super reactive. We add a proton, and now you'd have OF, and you have 1.5 bond order here and charge. The OF, we add an electron. You take and add an electron, it comes here. The one electron moves in there. You get OF minus. You take and add a proton to the oxygen here, and you get F2, and you take and add an electron, and you get F0 and F minus. So this would be a sequence as you go from N2 to F2, and then you add an electron, one electron, you're going to break these into atoms. So this would be the overall sequence.